right, today we're going to look at kinematics. This is the big quote unquote real world application of integral calculus. Just to recap for a moment, when we studied differential calculus, our big applications were optimization, when we wanted to maximize or minimize some particular function, and related rates when we had two quantities that were changing together and we wanted to know how fast one was changing when the other had a particular value or something like that. With integral calculus, one big application we saw already was volumes of revolution, although that doesn't feel particularly real life. It's often thrown in the applications chapter of various textbooks, and this is the big one. So kinematics is really just, it's from physics, as we see here, it's the study of motion. And those of you who are currently in a physics course or who have studied physics in the past, you'll probably feel comfortable with this topic right away. Most students of mine in previous years, when we get up to this topic, if they're in physics currently or have studied it before, they feel that this is just a very natural application of calculus, and they usually feel very comfortable with it right away. And going in the other direction, when they go back to their physics class, all of a sudden it's like, wow, why have we been doing physics without calculus this entire time? All of those kinematic formulas that you study in physics class, you can just throw them all away because you're often just dealing with simple functions that you can differentiate or integrate. Um, so calculus really makes physics way, way easier. So I hope that you find that this benefits you in that class as well. As we go through this, there will be no new formulas, really nothing new that's mathematical in nature at all. We really just need to get used to the language of physics and translating that into calculus. There'll be a lot of connections back to definite integration and areas underneath curves and all that good stuff, as you'll see. So let's begin. Before we even get into section A, we are given these 5 key vocabulary terms to make note of, and I'm sure that the wheels are already turning in your brains about how to connect these to calculus. I mean, we see accumulation over time, so that's reminding me of integration. We see rate of change down here, that's making me think differentiation. We'll be explicit about these points in just a few moments, but just a few things that you want to be able to keep track of in your head. There is a difference between distance and displacement. Those two are very similar terms, but they are different. And same thing goes for speed and velocity. Very closely related ideas, but slightly different, as we shall see. We will restrict our interest to motion that is one-dimensional. That is to say, we'll have an object moving along a straight line, and the displacement will give us a measurement of where that object ends up relative to where it began. So I wouldn't stress out about this point too much, but it is something to be aware of. Also in this example, we see that positive displacement is to the right and negative to the left. Of course, if we had a vertical axis, then we would interpret positive displacement being up and negative down. Those are the only two examples that you're really likely to see. I mean, any axis is technically possible, but those are the only two for which we have universally agreed upon orientations for positive and negative. Hopefully you agree that this first example is very, very easy. I mean, I could give this to a ninth grader as long as they know a little bit about quadratics, but I want to start here so we can just ease into things. Let's take a moment, read it, and I'm just going to put the answers up. Hopefully these make some sense. Okay, so some problems are really easy. We can answer them without using any calculus at all, and we've been solving problems like this for years. That's great. And we saw a moment ago the book's definition for displacement only use language about being right or left of the origin, but as I said, we're often going to have problems that really consider something moving vertically. There's another way that we can illustrate the motion of an object, which our textbook authors really love. It's called a motion diagram. Now, the IB would not require you to use one of these, but you may find it an effective way to communicate your work. This is a motion diagram for the stone in the previous problem, and you notice that motion diagrams, as the textbook authors like to draw them, are always going to be horizontal. And it is potentially a little confusing the first time you see it, but you could just as easily draw a vertical axis for displacement, and then you draw something that looks kind of like this. And really, that's not that different from the picture that we saw before. If it were me, I would just draw the parabola from the previous screen. It conveys the exact same information. I'm just bringing the motion diagram to your attention in case you've seen it before, in case it just feels better to you, and also since we will see it in the book's answers later on in this video, so I figured just get it out of the way. Anyway, now we're in section B, which is average velocity. And hey, we've talked about average rates of change before. That's just the slope of the secant line, and that's exactly what we see down here. As I said earlier, any distance rate time problem that you ever did in earlier algebra courses or elementary physics courses, it was dealing with the idea of average velocity. If we want to find the instantaneous velocity, guess what? We need to take our displacement function and then calculate its derivative. We will interpret a positive velocity to mean the object is moving to the right or up, negative that it's moving left or down, zero meaning that it is instantaneously at rest. Now, if you've really been paying attention, then it might seem that the textbook is contradicting itself because back in chapter 18, section C, it said that a function can only be increasing or decreasing on an interval, not at a particular instant. And so that meant that a parabola, for example, was both increasing and decreasing at its vertex. And in the context of physics, that would mean that our stone from the previous example was simultaneously both moving right and moving left at its highest point. No, I actually agree with the authors. They did give a perhaps unnecessarily advanced but technically correct perspective on increasing and decreasing functions. However, from a practical point of view, you will never be expected in an IB setting or an AP setting or whatever. No one wants you to say that an object is simultaneously moving left and right. No one wants you to argue that when you find that the velocity is positive at a particular instant in time, that, well, technically we can't say that the object is moving to the right because it can only be moving to the right on an interval, not at an exact point. Nobody wants to hear that. So impress them some other time. An important life skill sometimes is responding to the intention of a question rather than being pedantic about it. Don't be that person, okay? So quick check of understanding. We're given a displacement function here. We can find the average velocity by finding the slope of the secant line. We can find the instantaneous velocity by finding the slope of the tangent line, which is just calculating the derivative and putting in t equals 2. So, calculus, if we have a displacement function, we differentiate it, we get velocity. We take velocity, we integrate it, we get displacement. The change in displacement, or change in position if you prefer, is going to be the definite integral between the 2 points in time that you're interested in. Now, in most cases, you can pretty much get away with using the words displacement and position interchangeably, but now we do need to start being careful because displacement is not the same thing as distance traveled. When you go to school or go to work and then come home at the end of the day, your displacement is 0 because you ended up in the same place where you started. But obviously, you have traveled some distance. So distance traveled is going to require us to take the absolute value of the velocity function before we integrate it. Connecting this back to areas, whenever we have an area that is above the x-axis, we're going to interpret that to be a positive displacement. When we have an area below the x-axis, it'll be a negative displacement. So if we had some weird velocity function that was modeled by a sine wave, and we wanted to find the displacement of some object between time equals 0 and time equals 2 pi, well, then we're just going to integrate this. But since I know a thing or two about sine curves, I wouldn't really even have to bother. These two areas are going to be exactly equal to each other, except one's positive and one's negative. So the displacement in this case would be 0. The total distance traveled of the particle, however, in that case, I would need to consider this second area as being a positive one. You could either integrate from 0 to pi and then multiply your answer by 2, or take an integral from 0 to pi and then subtract the integral from pi to 2 pi. And that's the technique we will have to use if we have more complicated functions than where we can't exploit any sort of symmetry or other shortcuts. We'd have to work out where the function crosses the x-axis and then separate the problem into however many integrals the problem calls for. In this example, we'd have to do 4 definite integrals. We'd take the definite integrals for the 2 yellow areas, put those answers aside. Then we'd work out the definite integrals for the two green areas. Those are going to end up both being negative. We're just going to take their absolute value, call them positive, and then add all four of the areas together. Of course, if you've got a calculator handy, you just are going to use the absolute value function in there and then call it a day. If you've taken a basic physics course, you've probably seen problems like this. The velocity is not constant, but it is convenient enough. It lends itself to just working out some areas by using geometry formulas. In this example, since the velocity is always greater than or equal to 0, the displacement and the distance traveled happen to be the same thing. They're just not going to be any time that we have velocity being negative. Okay, so now we finally have a problem where we can think in terms of calculus a little bit. We have another quadratic function, but notice this time it's the velocity function that is a quadratic. In the example with the stone earlier, it was the position function that was quadratic. So in this case, we're going to have a cubic function for position. Part A, when is this particle reverse direction? They mean when is its velocity equal to 0? Well, velocity is a quadratic, so that's easy enough. It's going to reverse directions at 2 times, 1 and 2. From 0 to 1, looks like our particle is moving to the right. From 1 to 2, it's moving to the left. From 2 to wherever we want to stop, it's moving to the right. Part B, now look, our textbook is trying to get you to think about this problem in 2 different ways. I would just jump straight to what they're saying is the check here. I would just use the definite integral from 0 to 4 of the absolute value of velocity. As I noted just a moment ago, that means we're going to take the integral from 0 to 1. Then we're going to subtract the integral from 1 to 2, since that's the place where the velocity is negative, and then we'll add the integral from 2 to 4. Or I grab my calculator and I just type it in with absolute value. However, there is another way, making use of a motion diagram. You can take the antiderivative of t squared minus 3t plus 2. We're going to choose the initial displacement to be 0 because we're not actually told what the initial displacement is. So we'll just say it starts at the origin. It really won't make a difference in the end. We can then use our displacement function to figure out, well, in the first second, if we start at 0, where do we end up? Okay. Then we're going to calculate the distance traveled in that next second. We went from 5 over 6 to 2 over 3, so we can figure out how far that is, and then we can do the same thing for the next 2 seconds to get from 2/3 to 5 1/3. And that's exactly what we see happening in this diagram and with the arithmetic down below. Part C asked for the total displacement in the first 4 seconds. Thinking not in terms of calculus at all, we know the position at time 0, we know the position at time 4, we just subtract them, and we get the displacement. But of course, that is precisely what it means to have taken the definite integral of velocity evaluated from 0 to 4. When we integrate this, we're going to get the position function. We're going to put 4 in for time, and then we're going to put 0 in for time, and then subtract. The next step in all this is pretty straightforward. We're now going to talk about average and instantaneous acceleration. Acceleration is just going to be the second derivative of displacement. And I know that I always preferred this notation for a second derivative over this one because I personally was always confused about where the squareds go. But I want to point out that since you're comfortable, probably, hopefully, with acceleration's units being meters per second squared, that connects really nicely to this definition here. We have meters per second squared. All right, we can answer even slightly more complicated questions now. In this example, we have a position function, which is cubic. Part A asks for expressions for the velocity and the acceleration. That just means we're going to differentiate that cubic twice. Sign diagrams, again, very useful at being able to tell, just at a glance, of how the particle is behaving at any particular instant in time. Part B is asking us for the initial conditions. So we're just going to set t equal to 0, and then describe the motion of the particle at that instant. That just means we're going to give some statements about its position, its velocity, and its acceleration. So we see here, where is it located? It's 1 centimeter specifically to the left of the origin because its displacement function was -1. We know it's moving to the right because its velocity is positive, and specifically it's moving to the right at 9 centimeters per second. And then we also know what its acceleration is. Part C is asking for the position of the particle when it changes direction. Changing direction means that its velocity is going to be equal to 0. Its velocity function we just worked out, it was quadratic. So it's easy to see here that it's going to change direction at time equals 1 and time equals 3. And it's really easy to just think you're done then. But remember, the question was asking for the position when it changes direction. So we're going to take 1 and 3 and then put them back into the position function, giving us 3 and -1. Part D asks you to draw a motion diagram. Again, totally unnecessary, but it would look something like this. But mentally see if you can flip that around. You can kind of imagine taking the inverse of this graph, and you get something that looks like a cubic function, and that's precisely what the position function is. Part E was asking for the total distance traveled in the first 3 seconds. They're working this out from their motion diagram. We see that in the first 1 second, it travels 4 units to the right, and then the next 2 seconds, it travels 4 units back to the left for a total of 8. Again, this is equivalent to taking your definite integral from 0 to 1 minus your definite integral from 1 to 3, and that's the definite integral of the velocity function specifically. Look at one more real quick. This example, we are given the acceleration function for a train. They want us to find the velocity function and sketch it. Okay, that means we're going to integrate this. That's not too tough. It's an exponential function. We'll use a little bit of substitution. Easily done. We're going to have to work out what the constant of integration is. We are told that it is initially at rest, so we know that the initial velocity has to be 0, so we can work out what our c value is. And then we just sketch the graph of this exponential. That's not too tough. We know that it's going to have exponential decay, since our exponent is negative, and we know that it should be growing towards its horizontal asymptote because we are subtracting that term. Function transformations and all that good stuff. Okay, part B, how long is it going to take it to reach the speed 40? So we're going to work out when is this function equal to 40. And we can get an exact answer pretty easily, but I don't know about you, but I can't really calculate what the negative ln of 5 is in my head, so we'd have to grab a calculator and we would get this answer here. Of course, that's equivalent to what's going to happen if on our calculator we just graph the line y equals 40 and then calculate their intersection. We'll find t equals 160.9. That's how I would do that problem if I was finding a decimal. If I wanted the exact answer, however, I would need to use calculus. Part C asked how far the train traveled in that time, so from 0 to 160.9 or so seconds. So we're going to integrate velocity. We see that the velocity is never going to be negative, so the train's not changing directions. And we can keep the exact answers rolling pretty conveniently. If we put in 100 ln of 5 for t, then the e and the ln are going to cancel out from that term, which is pretty nice. So we can get this beautiful exact answer right here, 5,000 ln of 5 minus 4,000, whatever that is. Grab a calculator to find out its approximate value. Finally, we're into section D. We've got our last piece of vocabulary, which is speed. And for the most part, all we need to know about speed is that it's the absolute value of velocity. There might be some contexts where it's helpful to consider velocity as a vector because it has both magnitude and direction, whereas speed is a scalar. But for the most part, just knowing speed is the absolute value of velocity is all that we're going to need to know. We will often be asked to describe whether the speed of an object is increasing or decreasing. And to determine this, we're just going to consider the signs of velocity and acceleration. If they match, then the object's speed is increasing. We use the phrase speeding up. If they're opposite, then the speed is decreasing. We use the phrase slowing down. As a simple example, if you throw a ball into the air, its position can be modeled by a friendly parabola. While it's on its way up, its velocity is positive, it's moving upwards, but its acceleration, due to gravity, primarily, is going to be negative. So the ball is slowing down as it's moving upwards. When it starts to fall, now its velocity and acceleration are both negative. We say that the ball is speeding up, and we know that objects fall faster and faster and faster the longer that they fall. Even though we've seen stuff like this before, I think it's worth repeating. We can connect this back to ideas of concavity. So all four of these are graphs of position over time. In this first example, we see that clearly the graph is increasing, so the velocity of the particle is positive. The graph is concave up, which means that the acceleration must also be positive, because that's the second derivative. It's positive. Since these two match, the particle, object, whatever, is speeding up as it moves upwards. Down here, velocity is negative, it's going downwards. Acceleration also negative, because this graph is concave down. This object is also speeding up as it moves in the negative direction. Velocity negative, acceleration positive, again, concave up. This object is slowing down. This object also is slowing down. Its velocity is positive, but its acceleration is negative. They don't match, so we know it's slowing down as well. This might take a little bit of getting used to at first, but it's all vocabulary. There's nothing new mathematical about any of this. Okay, last problem for the video, I promise. Let's put all this stuff together, take a second, read through it, give it some thought, and then we'll jump in. I think in the interest of time, we'll just kind of race through this one. We've got a displacement function. Part A wants the velocity and acceleration function, so we're going to differentiate that twice. Velocity, acceleration, great. Part B, find the initial conditions, so we're going to set t equal to 0, put that into all three functions, and then it asks for a description, so we'll write a little sentence describing what we're seeing. Part C asks for the description at 2 seconds, so same idea, we put in t equals 2 to these three expressions. We see that the particle is 3 centimeters to the right of the origin. It is moving to the right with a speed. And then they note that since A and B have the same sign, the speed is increasing. Or we could just say that the particle is speeding up. Part D, just like before, it's asking for the position when it changes direction. So we're first going to find the time when it changes direction by setting the velocity equal to 0. We get t equals 1, and then we put that into the position function to find out that it's 1 centimeter to the left of the origin. Part E, again, not an IB type question. It's asking you to draw the motion diagram. The IB would never ask you to do that, but there it is. Part F asks when is the speed increasing, so when is the velocity and the acceleration have the same sign. For that, we look at our sign diagrams. You might say based on that that the answer is for t greater than 1, but the book's answer is t greater than or equal to 1, and this goes back to the whole function increasing or decreasing on an interval note from chapter 18 that I mentioned earlier. I did a little bit of research and I couldn't find any IB questions that asked about speed in this manner. I think that's probably intentional to avoid this issue. They don't like having ambiguity in their mark schemes if they can avoid that. So primarily they'd be asking things like, at this time, is the speed increasing or decreasing? Or when is the speed a maximum? Or something like that. So please don't stress out over that last point, or any point, really. It's not worth it. Life's too short, so relax.